Okay, we're about ready to start. Thank you very much, everybody, for arriving. And apologies that we took so long to get to this stage, because we should have done this session about 2 months ago, and I've just been too busy. So my apologies. It's been more than 2 months since our last meeting. So sorry about that. Hopefully this will be interesting for most people. We have some people from the Hyperledger meetup here as well. Great to see you guys, because you'll be answering all the difficult questions that we get related to Hyperledger. So anyway, let's kick off. What are we going to do today? We're going to talk a little bit about Hyperledger Fabric. We're going to explain the concepts behind Hyperledger Fabric and look at some of the components inside of Hyperledger. And then we'll do a demo. We're going to do a demonstration of a Hyperledger Fabric application. And then we're going to talk about what are the challenges of running this Hyperledger network on Kubernetes. I'm starting to think that this room has been very badly designed. With the door right over here at the front, it should be at the back somewhere. Okay. So let's get stuck in. Hyperledger Fabric concepts. So Hyperledger Fabric was formed around 2 or 3 years ago. It's now part of the Linux Foundation, and it was donated originally by these 3 companies here, IBM and so on. We had the first version about a year ago, in 2017, and we just released version 1.2 about a month ago, in July. So I wouldn't like to say it's a very mature product. It's reasonable, but it has a few issues. But it's getting better and better. Each release I see here, there's some significant improvements in that. Now, as I said, it's part of the Linux Foundation. The Hyperledger Fabric project is just one project under the Hyperledger umbrella. There are roughly 10 projects related to Hyperledger in the same group of projects. And they're not all blockchain projects. Some of them are around identity, some of them are around testing frameworks for Hyperledger and so on. So what is Hyperledger Fabric? It's a blockchain platform, but it is a private permissioned blockchain platform. Right? So it differs a lot from something like Ethereum or Bitcoin. Ethereum, Bitcoin is public and it's anonymous. Right? If you have Ethereum nowadays, no one really knows that you own Ethereum, and you don't have to tell anybody. You're an anonymous person on the network, and there's nothing private about your transactions. All your transactions are out there in the public. It's just that nobody knows that it's actually you. Hyperledger Fabric, fully decentralized, as is every other blockchain out there. It's an append-only blockchain, as every other blockchain is. The key thing is that it's an immutable ledger. Okay, all blockchains have this property. The blocks that are added into the blockchain are immutable. They cannot be changed. They cannot be deleted. Cryptographically, they cannot be touched. They cannot be changed in any way. That's why we have this whole expensive mining process in Bitcoin and Ethereum and other proof of work blockchains. It's all there to guarantee that those blocks can't be changed. We have smart contract support in Hyperledger. So it's called Chaincode inside of Hyperledger, but it's the same thing. It's really a smart contract that can be executed against the data sitting in the blockchain network. Hyperledger supports Go, Node.js. These are non-deterministic languages. Okay, so I'll talk about that a little bit later, just for the geeky people in the room who are interested in determinism and non-determinism. In Hyperledger, we can support non-deterministic programming languages. It's quite a difference to Ethereum, which uses Solidity. Solidity is a deterministic programming language. The end result of executing a Solidity smart contract is always the same, right? Where it is not always the same in these languages. I'll explain that a little bit later. Hyperledger also has a consensus mechanism, as does every other blockchain out there. This one is a little bit different. I'll explain that a bit later. It's really broken up into 3 different parts, but it's aimed at agreeing which transactions are valid transactions and what is the order of those transactions in the network. Okay, so that is Hyperledger Fabric in a nutshell. We're going to look at the components inside of Hyperledger Fabric. Now, all of these components that you see on this diagram here could actually run. Those guys taking photos, I'm going to upload this to the meetup afterwards, so you can download it from there. I'm going to share it, and I'm going to send it. I've already sent it to Edmund on the Hyperledger side, so he will share it with all the Hyperledger guys. All of these these components here inside of Hyperledger Fabric can run on Kubernetes. So the components that we see here, we see a certificate authority. In every organization in Fabric, there has to be a CA that is generating the identities and certificates for the members in that particular organization. We have peer nodes. Peer nodes, same as peer nodes in Ethereum. This is where the actual ledger state is stored. All right, so the state, the world state, and the blockchain ledger is stored on the peer node in every organization. Every organization can have 1, 2, as many peer nodes as it likes. Each peer node is storing a copy of the ledger. CLI is just a command line interface. You can jump into this container and you can execute commands against the Fabric network. This piece down here, ordering piece, this is where the transactions get ordered and grouped into blocks. And then those blocks are sent back to all of the peers in the network. I'll go through that process in a little bit more detail later. So why would you run Fabric on top of Kubernetes? The main reason we see is that it uses less resources. So Fabric has a very expensive, in my opinion, ordering component. All right? It uses Kafka to do ordering, and it is the most simplistic ordering mechanism you've ever seen. Basically, put a transaction onto a Kafka topic and then read it back off, right? And just read it back off in order. That's really all it's doing. And to do that, in production, you should run 5 Zookeeper nodes and 4 Kafka nodes. So you need 9 EC2 instances just to run a very, very simple, basic ordering component. And when you tie the ordering service nodes on top of that, which actually do the creation of the blocks and send those out to all of the peer nodes, plus the peers and the CAs and everything else, you could be using about 16 EC2 instances just for the one member of the network. Then the next member of the network would probably run peers and a CA and maybe a CLI. So they could be running 2 or 3 or 4 instances. It all adds up to a lot of instances. You can do it a lot cheaper running it on Kubernetes. A much smaller amount of instances could save you a bit of money. And obviously, besides that, there are a number of companies where Kubernetes is the de facto platform for running all of their applications. They like to run everything on top of Kubernetes, including things like Fabric. Anyway, enough theory. Let's actually look at an application running on top of Fabric, on top of Kubernetes. But before I do that, let me just tell you what the architecture looks like. So the way I've designed this little demo that we're going to see is, on the left-hand side, we have an orderer organization. So inside of Fabric, this organization is simply responsible for ordering the transactions and sending those transactions to all of the peers in the network. It's running its own Kubernetes cluster. It's in this case, US West 2 region. It's in one of my AWS accounts. In my other AWS account, in a different region, US East 1, I have some peer nodes. And these peer nodes are receiving all the blocks of this ordering service component, storing them in their ledger, and making them available to this application, which is the Marbles application. Marbles application is a Node.js application. It connects to the peers running in this account over here, and it displays the state of the network on a nice user interface that you'll see in a minute or two. So this is a pretty standard Fabric network. All right? Most Fabric networks, if you're going to run them in any type of production deployment configuration, would look like this. An orderer located somewhere, and a whole collection of remote peers, potentially in different countries, different cloud platforms. Some of them could be on-premise, off-premise, but they're all related to each other in this network. And all of them are getting copies of the blocks coming out of the ordering service node, and all of them are storing their own copies of the ledger here. So that's a pretty typical Fabric network. Okay, so let's have a look at the application. I mentioned that it's a Node.js application. Right? So Node.js application is for David. You're an expert in this, right? Because you contribute to this SDK. So the Node.js application here is using the Node.js SDK to connect to a Fabric network. David knows a lot about that, so if you have any questions, you can ask him. He contributes some of the code to this. So it's just using a standard SDK. It's connecting into various points in the Fabric network, which I'll explain on the next slide. And it's pulling out information from the network, and it's displaying the state over here. So let's take a look at this application, which I have running here. Now, just give me a second to restart it. For some reason, it loses the connection after a couple of minutes of nothing happening. I haven't got around to figuring out why just yet. Okay, so what we have on the screen then, let's just refresh this page. And this page. Okay, so notice the URL up here. It says localhost. So this application, this Node.js application, is running here on my laptop. Right? It's connecting from my laptop into the Fabric network, which is running in US East 1 and US West 2, US East 1. What I also have is I have another copy of the application, which is running in US East 1. It's connecting to a different Fabric peer node in US East 1. So I have two copies of the application connecting to two different peers, but they're all in the same network. Okay. And what we'll see, if we, let's say we do something on this page here. I'm not sure if, did any of you guys play marbles when you were young? I used to play marbles a lot. But I had to win all my marbles the hard way. Brendel over here, he had a rich dad, right? So his dad used to buy him marbles. But all of these marbles I've got here, I won them fair and square with this guy. So, and here's another one, just won another game of marbles. And what's happening here is a marble is being transferred from Brendel to me. And if my application is still running, then that should go to be fine. So if you look on this page, which is the other application that's running, this is showing a copy of the blockchain network. And you might see that that yellow marble just actually hopped from Brendel to myself. So even though I did the marble transfer over here on my local host, on my version of the application, which is pointing to a particular peer running in US East 1, this version of the application running in also in US East 1, but a different peer, is seeing exactly the same state. So you can actually think of this marble here as just an asset. It could be a house, it could be a car, it could be a coin, it could be a cryptocurrency coin, right, that I'm transferring from one person to another. And I transfer it on my peer, and within 2 seconds or so, everybody else is seeing the same state, right? In Fabric, it's probably around the 2-second mark. So as far as I remember, the blocks in Fabric are cut every 2 seconds. So that means when I do a transaction, it gets sent to the orderer. Every 2 seconds, a new block comes out, it gets sent to all the peers, and they then reflect the state here. So I could do it the other way around as well. I could move another marble from here to there. Oops, that wasn't a very good demonstration. Okay, and then the marble appears here on this particular peer, because this peer has received a copy of the block and is now updating the UI based on the state in the local database. Let me just show you what happens behind the scenes a little bit though. So this little demonstration here, this little box here, is showing you what Fabric does behind the scenes when you do an asset transfer. Like when I do a marble transfer from one owner to another owner, it says here that the first thing that happens is the client application, the Node.js application, is taking that marble transfer and it's sending that to all the peers that need to endorse the transaction. So there's a whole bunch of peers in the network. They need to endorse the transaction and say that they're happy with that transaction. They need to digitally sign the transaction to to approve it, basically, and say we're happy with that transaction. So it gets sent to all of the peers, they endorse it. That can get sent back to the application over here, they package it up in a nice little package, and it gets sent to the ordering component. The ordering component does a massive amount of work, right, by taking this package, putting it onto a Kafka topic and then reading it off the topic on the other end, putting that into a block and sending the block back to all the peers. When it comes back to all the peers, they simply update the world state and their blockchain, and that's the end of the transaction, after they've done a little bit of validation and a few other things. Now you can equate this to what would happen in a normal database. Imagine you had a normal MySQL database and you just wanted to add a new row, right? So you'd have a piece of code that said something like begin transaction, insert row, end transaction, and you're done. Right? That would be the end of it. This is really the equivalent of that, but it's done in a distributed setting, a distributed network, with cryptography to make sure that the chain is completely immutable, and to make sure that the change happens on every single peer in exactly the same way. So it's doing the same thing, but it's trying to solve a very difficult problem, which is doing this in a distributed setting. Okay, so that is what Fabric is doing behind the scenes. So let's get a little bit geekier and have a look at what it looks like inside the log files. So what I've done is I've got a search here that's searching on the word block. I'm just going to show you what happens here when a new block comes along. Do you think somebody could fiddle around with those lights over there and see if they can turn off these front ones? Give it a go. What's the worst that can happen? Thanks. That's great. Okay, so here we get a new block coming to the peer node. The peer node has to do some validation for this block. Okay, so here we have a new block number 62, coming to this peer node, and the peer node has to start validating the block. What the peer node has to do has to check the digital signatures on all of the transactions inside the block and make sure they match the endorsement policy. Right? Make sure that the digital signatures are correct. It's quite an intense piece of work, actually. It's quite CPU intensive, quite expensive, but it has to go through all the transactions and check all the digital signatures. So it goes ahead and does that first. Right, and then it gets to a point here where it's finished the completion, it's completed the validation, and then it has to do a interesting piece of work here, which is fine. All right. So you know most databases have a locking mechanism, right? So databases do pessimistic locking, or they do some type of optimistic locking. Optimistic locking is very simple. You read a row out of a table, and you also read the timestamp, right? Read the timestamp with the row. And then when you come to update that row, you update it if the primary key matches and if the timestamp matches. If the timestamp doesn't match, you reject the update. This is a way of doing optimistic locking. Hyperledger Fabric does something similar. It calls it multi-version concurrency control. But when you endorse a transaction, it reads all of the data out of the world state database, which is a CouchDB database in this case, reads all the state out of there, and it stores it in the transaction. It gets sent to the ordering component, and eventually comes all the way back to the peer in the form of a block. Fabric then takes all the data, out of the message, and it compares it to what's in the database at that point of time. If it doesn't match, the transaction is rejected. So this is Fabric's way of solving this double spend problem. Not sure if you guys are familiar with Bitcoin, but Bitcoin was really the first thing that came up with an algorithm that solved the double spend problem. And that is, how do you make sure that one Bitcoin is not spent more than once at the same time? What's to stop me sending one Bitcoin to you and to you at the same time? Right? Bitcoin algorithm has to prevent that from happening. And the way it does it at the moment is it builds in this big delay, right? It has a mining process that takes about 10 minutes to mine a block. So it builds a delay into the network so that everybody in the network can synchronize their state, so that it's impossible for me, or not impossible, highly unlikely for me to actually take a single Bitcoin and spend it twice. If I do that, someone in the network is going to catch me out. Now, Hyperledger doesn't have that benefit, right? It doesn't have the ability to wait for 6 blocks to process, which is 1 hour in Bitcoin terms, 6 blocks to process before it can confirm that a transaction is right. It has to confirm the transaction immediately. So Hyperledger does it this way. By writing all of the data into the transaction at the point that the transaction is read, and then comparing it at the time that it actually commits the transaction to make sure the data hasn't changed. That way it guarantees that the same particular record has not been updated twice at the same time. So it's a way of solving the double spend problem, but it's a completely different way of solving it than Bitcoin solves it today.
It's not a safe.
Okay, so that's what it's doing here. It says it's comparing the versions. It reads the records out of the CouchDB database, compares all the versions, and if they're fine, it updates the world state, and it updates the blockchain, or the ledger, with the latest information. If they're not fine, that record will get rejected, but it will still get written into the ledger, right? So the ledger contains valid transactions plus invalid transactions. They just get marked with a tag to say that it's a rejected transaction. Okay. So I think that's enough on the block files. Okay, so let's get down to Kubernetes. What are some of the challenges in running Hyperledger Fabric on top of Kubernetes? The first one is this. A peer is a pet. Some of you guys are familiar with this whole idea of pets and cattle, right? If you have a pet, like a pet dog, he has a name, you feed him, you love him, you take him for walks, etc. But if you fancy a steak and there's 1,000 cows in the field, you just shoot one and you carve a piece of steak, and there's another cow. There's plenty of those. So you don't care so much about cows, but you care a lot about your pets. So peers are pets. You can't just kill off a peer, right? He's got an identity. For goodness sakes. He's got a name. Actually, he has a lot of data inside of him. He has private keys and all sorts of things in there. You kill him off and you lose all of that. Like all the data's gone. The ledger's gone. You've lost the private keys, you lost the identity. You killed off a friend here. So Kubernetes is not the best at handling stateful data. All right? It's working on ways to do it better. It obviously has it's pretty good at handling things like the Sandra databases or Kafka clusters and all that, where things need to start up in particular orders. But it's not so great at handling things like Hyperledger peers that have state. Peers are non-fungible. One peer does not equal another peer. Okay, you can't just kill off a peer and start another one. It's not that simple. So this is a slight problem inside of Kubernetes. Let me give an example. Guess what happens if you start a new peer on Kubernetes and you join that peer to a channel? Well, it has to replicate all of the blocks from the beginning, from the Genesis block for that channel. It has to replicate all of those blocks from other peers and from the ordering service node. It has to build its own ledger and has to build its own world state. And it does that in exactly the same way your traditional database will do database replication. It starts from the beginning and it applies every single transaction in order. Right, so it has to do that. That takes a bit of time if you have a big ledger. This world state, just to give you a bit of background, this world state is sitting inside of a database. In Hyperledger is either a level DB database or a CouchDB database. I think David did a presentation where he actually proved that running it in a level DB database is much faster.
Yes, okay.
It's a lot faster because the database, the level DB is sitting here. Right? There's no network call to get to the database, and it's sitting on the file system. And it's a file system database. Whereas CouchDB really is a proper key value store with its own API. It's sitting in a different container inside of Kubernetes. They're running in two different containers in the same pod though. So there's still a local host call here. But it's still a network call, even though they're running in the same pod and on the same host. I typically use CouchDB because it has some rich query capability. You can do much richer queries against key value store in CouchDB than you can against LDB. But it is slower, as I remember from David's talk. So, like I say, those transactions all come here. One by one they get added to the ledger, and one by one they get added into the full state. And that means that by the time this guy's finished, he has exactly the same information as this guy. Exactly the same order, they're identical. Because this piece is deterministic. All right, we talked about determinism before. The replication of data to other peers is a deterministic process in Hyperledger Fabric. It always works in the same way, and peers will always build the same copy of the ledger. But if you delete a peer, well, you lose everything. Right? You lose all the data because it's typically stored inside the pod. Once the pod's gone, all the data's gone. So how can you fix that? Well, you can externalize the state. So you can mount an EBS volume, mount that using persistent volume into the peer, install the ledger in one place and the world state in another place. And if your peer dies and you restart it, it should start in the same availability zone as it died in. All right? Kubernetes is supposed to guarantee that. And maybe the Kubernetes gurus will correct me, but I'm not sure if I'm 100% right here. But I think one of the first things that Kubernetes scheduler does when you start up a pod is it makes sure that the volumes you're attaching to that pod are in the same availability zone as the EC2 instance it schedules the pod onto. Right? That's part of the filtering process it goes through. So the scheduler should make sure that when you start up your peer again, it's in the same availability zone as the EBS instances. Because for some reason, EBS instances in AWS are pinned to an AZ, right? So you have to start up in exactly the same AZ as you died in. You can't start up in another one. If that doesn't work, obviously you can use Affinity to solve that problem, right? You can use Affinity or taints and tolerances inside of Kubernetes to make sure that your pod starts up in the same zone as your EBS volumes. We talked a little bit earlier about what happens if a peer crashes. Kubernetes is fantastic at making sure that your pod's always running. Pod dies, Kubernetes will start it up again very, very quickly. It notices that it's down, it'll start it back up again. But because a peer is stateful, has identity and all these sorts of things, it's not really that easy. So look at this long process that it goes through. You know, if you start up a peer in Fabric, it's not attached to any channel, it doesn't have any identity, it doesn't have any data in it, it's useless, basically useless. It has to go through this whole process. It has to enroll with a CA to get some identity, generate some certificates. Then it has to use the channel genesis block to actually join the channel. When it joins the channel, it gets the details of the ordering component, connects to the orderer, starts synchronizing all the blocks. You have to install some Chaincode on it, otherwise you can't execute any queries or transactions on it. And then it has to build a copy of its own copy of the ledger. This takes a bit of time here. So restarting peers, it's not as easy as it is with stateless applications. You know, if your Nginx server just crashes, you just pop up another one, and within half a second it's ready to go. This could take quite a while, actually, depending on how big your ledger is at that particular time. So here's another gotcha when running Fabric on Kubernetes. I mentioned before that the world state inside of Fabric is stored in a different container, right? So this runs in a different container inside of Kubernetes to the peer container. So the peer container, the CouchDB container, they run in the same pod, but two different containers. And they're obviously linked by localhost. So these queries here are pretty quick. They're guaranteed to be on the same EC2 instance, right? They're on the same host. And over here you have the actual chain code. Right? This is the smart contract that you write, and it has to execute somewhere. So in Fabric, it executes in a Docker container. So we have 3 Docker containers here: HostDB, Peer, and this guy here. There's also system chain code that handles the lifecycle of chain code and all the endorsement policies and so on. This is a little bit different. It's actually baked into the binaries of the Peer, right? So this is specific to a version of Hyperledger. You can't change this very easily, right? It's baked into the Peer. But this one here, this is what you write yourself. It runs in a Docker container. When I say it runs in a Docker container, it really does run in a Docker container. It doesn't run in Kubernetes at all, right? Kubernetes doesn't even know about this guy. So this Peer here starts a new container using Docker commands, and we end up with a Docker container running here on its own, under the control of the Docker daemon, that Kubernetes doesn't know anything about. And the problem is, this chain code has to communicate with this Peer. But obviously, this chain code doesn't know anything about that Peer, because they're running in 2 completely different environments. To make it even worse, this chain code here is not allowed to access that data directly. Right? It needs to query the world state, but it can't do it directly. It has to do it via a shim, like via a proxy that's sitting here in the Peer. So it really needs to get through that Peer to that data over there. So there's 2 ways of doing it, and neither of them are particularly nice. Okay. The one way is you pass some argument to the Peer. When the Peer starts the user chain code container, it passes the IP address of the Peer. And then the chain code container will communicate with the Peer on that IP address. So that's one way of doing it. The other way of doing it is even less pleasant. And that is, Docker has its own DNS configured, right? Inside the Docker options of the Docker daemon, it has a DNS configuration there. And I think it typically points to the Google DNS or something like that. You can change that DNS to point to the Kube DNS. So what you have to do, you have to go into the host of every single Kubernetes worker node. You have to change the Docker options so that the DNS used by Docker is now pointing to the Kube DNS. And then it will look up the location of the Peer container using the DNS name in the Kube DNS, hopefully find it, and then be able to communicate with this guy. There's been a change request out with Hyperledger for quite a while now to do something about this. I don't really know what the solution is, but this is a little bit messy. So I've tried both ways, they both seem to work, but neither of them is particularly nice. It would be much better if this was under the control of Kubernetes, and it would all be one big happy family.
I mean, is it possible you just spawn a new pod and then you communicate to the, I mean, when the Peer container is trying to run a user container?
The thing is, we don't control this.
Okay.
So the creation of this chain code container is handled by the Peer binary. Right? The Peer binary, the actual code of the Peer actually creates this container. So we don't have any control over that. I suppose what we could do, we could actually check out the Peer code from GitHub, and we could change it so that it spawns a Kubernetes container. That's one option. But natively, there's no easy way to do that.
Yeah, I mean, because you're running the Docker out of the Kubernetes,
yeah.
Do you afraid to lose all the smart contract content after the contract is just died?
So that container there can die, right? It can disappear. It doesn't hold any state, so we don't really care if it dies. If something goes wrong with the container, the Peer container will just start another one. So it takes about 20 to 30 seconds to fire up that container. So the very first time you do a query in Hyperledger against a particular Peer, you'll wait maybe 20 or 30 seconds while it's downloading and creating this particular container, and then it will execute your transaction. And after that, it's really fast. If that container dies, it'll just fire up another one, and you might have to wait 20 seconds. But there's no danger in actually losing that. It doesn't hold any state. All the state is there and there. So this is just the code.
I have a question that what did you say you run on different Docker container outside of the Kubernetes? Why don't you use the static part?
The what?
Static part.
static path, how is that going to help me? Because what I need here is I need this container to hook up and communicate with this container. So it needs an IP address.
Okay.
It needs an IP address. So a path isn't going to help. It needs an IP address so that it can send requests. I'm presuming it's gRPC, right?
Yes.
gRPC between this container and this container here. So it needs an IP address to communicate.
Oh yeah. Just to be clear, the chain code is only ran on one node, right? And then it sort of communicates like a simplified like data changing instruction set to the rest of the peers, or is it spawned on every single node?
Every single peer node will look like this.
Oh, so
Every single peer will have its own chain code.
got you. And have you guys had any issues with like VM escapes in Docker? Because I can run whatever I want. Can I just like make a Docker image and then like give it to you, or?
No, because the Docker image that is used here is built into this binary. So you have no control over it.
Oh, got you. Okay.
So this binary actually in the code starts this chain code container. It's not configurable.
Okay, so I don't.
Unless I'm wrong, but as far as I know, it's not configurable. It's
Okay.
hard coded into the binary of that container.
Okay, got you.
You can't change it.
And what make it worse is even you kill that container and save the image and restart it, the resumed container of the chain code cannot be recognized by the peer.
Okay. So they built some security in there to
Yes.
make sure that only that container started by that peer node can actually. They use TLS, right? Also in here, they use client-side TLS here to make sure both of these sites communicate with each other. So I guess they have some really strong security to make sure that only a container started by this guy can actually execute the chain code. Yeah. Yes.
Does this mean that the peer container is run in privilege mode inside Kubernetes?
Is it run in privilege mode? I don't know actually.
Okay.
I'm not sure.
Because it seems to be able to communicate directly with a Docker daemon, so it should be able to.
Yes.
Or it should be running in privilege mode.
I haven't actually checked that. I don't recall seeing any setting inside of the peer YAML to say that it is running in privilege mode.
Okay.
But maybe I haven't looked at it close enough. But you're right. I mean, it is actually using Docker commands to start that document. Possibly. In which case, it wouldn't work on some platforms like OpenShift, right, which don't support those. Potentially. Okay. So related to that issue, what happens if your chain code fails? Right, so your chain code fails in this Docker container. How do you actually find out what went wrong? So, two options. First option, SSH into the Kubernetes worker node and just do a Docker logs. That's one option. But that only works if you actually have a key pair that you can use to SSH into the Kubernetes worker node. If you're like me, I never really bother about the key pairs because I don't expect to SSH in, and then I've got no way of finding out. But it turns out, if you configure your peer with this particular environment variable here, it'll actually send all the logs from the chain code container to the peer node and not appear in the peer logs. So you can see them in the peer logs. So thank you very much to the Hyperledger Fabric people, because that saved me a lot of hassle. Sure. Okay, we're going to talk a little bit about high availability. So, you think that high availability in Kubernetes is easy. You just run two pods in different availability zones with some type of load balancer across them, and fantastic, you have high availability. You can't really use load balancing so easily with Fabric because these guys have identity, right? I want to send messages to a particular peer, and a particular peer needs to communicate with another particular peer. You can't just load balance those requests across random peers. It doesn't really work so easily that way. Also, the other thing is, just to make it a little bit worse, there's different types of peers. You know, there isn't just one peer. We don't just have a peer. We have endorsing peers. We have anchor peers. We have leading peers, and they all have to be handled a little bit differently. Maybe starting to see that Fabric is quite complicated, actually, and running it on Kubernetes, there's quite a few things you have to think about. So here's some examples. Let's say your peer is an endorsing peer. By endorsing peer, what I mean, that peer has to digitally sign transactions before they're sent to the ordering component. So that means the application, like in this case the Marbles application, has to send those transactions to all of the endorsing peers based on the endorsement policy, and they all have to sign it. If there's no endorsing peer available, the transaction fails, right? It's not going to get signed by anybody. And if one endorsing peer is missing and he has to sign the transaction is going to fail. So it's quite important that they are highly available. And it's quite easy to do this. We just simply run two of them. Right? We run two endorsing peers for the same organization, different availability zones. So that one's not too difficult. Leading peer, a little bit different. What is a leading peer? Let's imagine a Hyperledger Fabric network with 100 members, and each member is running 2 peers, so we have 200 peers. That means every single block has to get sent to 200 peers. So the ordering component has quite a load on it, right? Because now it has to send blocks to 200 different peers. It has to establish communication links with all of those peers and send those blocks to all 200 of them. So that gets quite expensive, and it gets quite slow because you have a bit of a bottleneck now to this ordering component. So was it maybe in version 1.1, I think? When did Gossip come out? Was it 1.1?
In 1.0, they are already Gossip.
Okay. So now we have Gossip inside of Fabric. Gossip is a protocol that's used in many distributed systems, right? Used in Cassandra, for example, to distribute, to replicate the state and to replicate the rows or the data in the database between the different nodes. So Hyperledger Fabric also uses Gossip. What happens is the ordering service node only needs to send the blocks to the leading peer in each organization. So instead of having 2, 3, 4 connections, he only has 1. It goes to only to the leading peer. And then the leading peer uses Gossip to send it to all the other peers in the same organization. So they almost get updated in a 2-phase type of approach. First they go there, and then that guy distributes them to everybody else. Now that's all well and good, but what happens if that guy fails? Well, if that guy fails, there's no leading peer, and that means that organization is not going to get any blocks at all. So what we have is we have a leader election process that happens here. Right? So these peers are obviously communicating with each other all the time using Gossip. Gossip's very good for communicating state, making sure the peers are alive and so on. And if this peer notices that that peer's gone, an election process happens, this guy becomes the leader, and this order of service node will now send the blocks here. Right? So that's taken care of by Hyperledger Fabric natively, nothing we need to worry about. All we have to do is set the right environment variables on the peer to make sure that this leader election process happens. And then we get to the most confusing type of peer, in my opinion, which is the anchor peer. If you read the documentation in Fabric, what is the purpose of an anchor peer? Anchor peer in one organization, like this one, communicates with an anchor peer in another organization, and it communicates the state of the network. What peers have joined, what peers are dead, what new organizations have joined, etc. So everyone now knows the state, the entire state of the network. So that's all well and good, but the problem is that these anchor peers, the addresses of these anchor peers, are encoded in the Genesis block in the channel, right? They're fixed into that Genesis block. So every peer that reads the Genesis block and joins the channel knows which peers are the anchor peers. But what happens if the anchor peer goes down? Well, if the anchor peer goes down, well, that's just tough, right? He's gone now. There is no other peer that can replace it. You have to restart an anchor peer on the same address endpoint, because that's the address endpoint hard-coded into the Genesis channel. So I don't think there's another way around that, unless you guys know something better.
But more complex.
More complex.
Because you can reassign and compare.
Yes.
But it is related to block sync.
Or you could actually write a new configuration block into the channel with a different endpoint. right? But if you've seen the process for writing new configuration blocks into the channel, you probably wouldn't want to do that. It's quite complex. So I think maybe they will sort this out in a future version. And there's also some questions about what the anchor peers are used for. Now, I said that the documentation says they're used to communicate state. I've read a few things in the Hyperledger Fabric Jira and so on. But some of them say, yeah, that's what it's used for, but actually the whole network can live without anchor peers. I don't know for sure. I always encode them in the Genesis block, and it always seems to work. And in fact, when it can't find the anchor peer, there's always these error messages here in the log file. But I'm not sure whether it would actually work without the anchor peers. I don't know how they communicate state with each other. Okay, I've talked a lot. Just a few slides to go. So this is one of my big complaints about not just Fabric, but almost every technology you see out there. Whenever you see an example or a tutorial about how to run something, it's always such a simple, stupid scenario that you can never actually use that in real life. All right? And the same goes for Hyperledger Fabric. All the tutorials you see about Hyperledger Fabric create a network that looks like this. Order a service node, a couple of organizations with peers in them, and they're all co-located. They're all running in the same place. Typically, they're all running on the same EC2 instance or the same virtual machine, and they're started by Docker Compose or something like that. Everything is co-located. Okay, so that is absolutely not a distributed blockchain network. All right, that's a toy that you can play around with. You can play around with some smart contracts, get the feel of how it works and all that. But you would never, ever, ever put something like that into production. Okay? There are compromises, security compromises everywhere in the network. So you would never do something like that. You might think that this would be better. Okay, here we have an organization which has the ordering component. And here we have a peer which is separate in a different organization. And here we have some other peers that are also separate in different organizations. And to me, this is getting closer to what a fabric network should look like, except there's a bit of a conflict of interest over here. Especially if those two pieces are being run or owned by the same legal entity, same organization. Because all of the consensus mechanism of Fabric is housed in these components here. Okay? Fabric has got a consensus mechanism that's completely different to Bitcoin, Ethereum, all those other ones. Made up of 3 parts. First step, every transaction must get endorsed and digitally signed by other members in the network. That's the first step. That's done by these guys. Second step, every transaction has to get ordered and grouped into blocks. That's done by these guys here. And the final step, every block has to get validated, and the read-write set on every block has to get checked to make sure the data hasn't been changed. That's done by these guys here. So imagine if you had a network where you owned these components over here, and you had a pretty weak endorsement policy that said any organization in the network can endorse my policies, endorse my transactions. This guy could endorse, order, and validate all the transactions in the network. That's a bit of a security gap there. So you want to make sure that that doesn't happen. And the way to make sure it doesn't happen is to completely separate these and make sure that these are owned by different legal entities. So what happens typically in a production network? The ordering component here is owned by a joint venture, a consortium, some other type of legal entity that might be made up of other members of the network, but it's not owned by one company. Right? If it's owned by the same company that actually has endorsing peers, there's a conflict of interest there. So you need to structure this network along the same lines as your legal entity boundaries are in your actual real-life organizations to make sure we don't have a conflict of interest here. In this case, transactions get endorsed by organizations that are outside of this organization. They might be part of the legal entity structure here, but they're not solely responsible for this piece. It's like, everyone talks about blockchains, public blockchains, and how decentralized they all are. And then when you look at something like Bitcoin or Ethereum, and you look at all the miners for those networks, they're all grouped into three groups. Like Ethereum, 60 or 70% of the network is mined by 3 different companies. 3 companies own basically the entire Ethereum network. That's not decentralization. Okay. And you have the same problem here if you have the same organization owning these pieces. It's not decentralized in any way. So you need to make sure there's complete separation between these components. Otherwise you have no integrity in your network. You have this fantastic technology, but there's just no integrity there.
I have a question.
Yes.
Only the organization 0 can deploy the Kafka, right? So can I deploy the Kafka into different organizations?
No, there's only one. You can have multiple order of service nodes. So I could have an order of service node here, like I've got one here. That's okay. But there's only one orderer component, and that is the Kafka cluster. And that is sitting in one location.
Okay. What if that Kafka is down?
Kafka should be highly available. So
Should be, but what if the whole?
if it's down, the whole thing is dead. Right?
Okay.
Nothing's going to happen. So that's why you always run this highly available. 5 Zookeeper nodes, 4 Kafka nodes to make it highly available across 3 different availability zones. It's you have to guarantee that this thing is up the whole time. Otherwise, your network is dead.
Sorry, it is 5 plus 4 recommended.
Yes. You'll find most people will recommend running 5 Zookeepers, and to make sure you don't have too much of a split brain scenario. And also because many cloud providers like AWS support EBS volumes that are pinned to availability zones. So you need to run 5 Zookeepers with different types of persistent volume setups. I typically run 3 of them with EBS volumes and 2 of them with ephemeral storage. So that's the typical setup.
So maybe I didn't understand correctly, but is the idea that you need to have one centralized entity, and the way to make it decentralized is to just have it be owned by a legally decentralized entity? Because like who SSHs into like the org0, or who sets up the cloud environment,
Yes,
right?
yes.
Like who owns the AWS account?
Yes, so there's the AWS account is owned by the legal entity that owns this piece.
But
And
isn't
that
that
should
kind of
be made
cheating?
up of more than one organization. And the organization members should agree amongst themselves who are the administrators of that particular component.
But wouldn't like one use case of like Hyperledger to like run one of those decentralized organizations that operates an AWS account? Isn't it like kind of, you see what I'm saying?
Yeah. We've even had customers talk to us and say, because each of these organizations have to run a certificate authority, would it make sense to actually have an organization that's offering a service, which is a certificate authority service? So yeah, it would make sense for organizations to offer some type of root CA service. Also makes sense maybe some organization would run the central ordering component. And that organization would be completely outside of this. The question is, who will these organizations trust? So it all comes down to trust, right? Who are they going to trust to run that? Would they trust AWS? Would they trust somebody else? If we can figure out who that person is, then that would be the perfect company to actually run that. And I would love to see it that way. I'd love to see that this was a completely separate component run by somebody else.
Because could you make it so that the orderer would like, everyone runs an orderer, and then they kind of like sign the final state of the orderer and then send it to the real orderer, which will only, you see what I'm...
Better talk to the Hyperledger guys. I don't know.
All right.
But yeah, they are trying to change the consensus mechanism inside of that. They're trying to turn it into a Byzantine fault tolerant consensus mechanism. It is not one at the moment. Some people say that it is. It's not. Right. It is not Byzantine fault tolerant at the moment. You can configure this in so many different ways that it's certainly not BFT. This is CFT, crash fault tolerant, which is similar to Paxos or Raft or any of those type of consensus mechanisms. The whole network itself, you could try and configure it to be BFT. It isn't really, but they want to try and actually create a consensus that is fully BFT. And I think I've seen some test results on that. So it obviously is there, but it's not available to fully plug in. Do you guys have any further information on that?
Yes, about just a pen, because actually it is possible if each organization of different party or companies, they can own their own instance of CCA. Then they have their own root certificate. How does this different root certificate communicates, because there's a special terminology in Fabric, this called channel. Yes, and even one comment, because one of my teammates, they have, so they do some experience that Kafka can be distributed in different physical machines.
Yeah.
Yes, maybe you have to try, but I'm not sure because these different my teammates. Yes.
You know, absolutely. Fabric can be fully,
Kafka
can be
shipped
fully
by different organization or just the same organization?
You can manage my different organization, and different organizations have their own set of bootstrap scripts, setting their own certificate, setting their own peers, setting their but on order is not possible because multiple orderer organization inside a channel is so far not supported. So in this case, the orderer 1 and orderer 3 can only be sharing the same root CA. So far, because that's the one tricky thing that not all been solved so far. But I have created an issue for that, but there's no reply so far. Yes. Otherwise, there's if theirs can be fixed, then another new organization create their own sets without any permission from the org 0 is okay.
Yeah. So I think that sort of summarizes that Fabric is really still in development. Like there are some things that are not easy to do, and they'll get better over time. I mean, the gaps between 1.0, 1.1, 1.2 is quite significant. There's a lot of improvement happening in Fabric. So it's not perfect. We're working around all the imperfections at the moment, but it's certainly getting better. Yeah.
So what factors can decide the size of Kafka clusters? So is it the number of peers or TPS?
Yeah, so this guy over here, these have to send the transactions out to all of the leading peers. So depending on how many organizations there are and how many members or peers in each organization that it has to send transactions to, you might end up running multiple copies of these. And also the logic inside of here is actually to take the transactions from here and to group them into blocks. And every ordering service node has to do that, has to run the same piece of code. So I don't find that these nodes have to be particularly big. I find most of the processing power is here, especially in the transaction validation. That's really expensive on the CPU. So it's more important to get the sizing of these things right. These things can be scaled horizontally, and I won't go into too much detail, but you can have as many of these as you need based on how much traffic it has to disseminate. But these guys here are probably the most important to get the sizing right.
So the minimum size for Kafka cluster should be 4, and for Deeper 3.
Well, that's the minimum. If you're running it in production, we always recommend 5 or 4. I always run these using instances that have more CPU and less memory. So make them more like C instances that are more CPU focused rather than memory focused. Most of the processing here is CPU intensive.
Question.
Yes.
So is Hyperledger actually decentralized?
It's decentralized.
Because it is still centralized.
Except for this
in
piece
case.
here. Except for that piece. But this piece only does ordering. The consensus mechanism is split up between here and here. So it's not like some blockchain networks where the consensus mechanism